again, and this is a recap of what we saw last time, and we consider quantum quenches of global Hamiltonian parameters in spin chains, essentially, and we define global quenches or quantum quenches. Essentially means that you imagine to prepare the state in the ground state of some Hamiltonian, which can depend on some parameter like the magnetic field. Then you, at some point, you change the value of that parameter abruptly, and you start the time evolution. And then we define, we ask ourselves how can we define relaxation in these systems. And one answer was, well, we can define a weak form of relaxation as a time average. And we have seen that the limit of infinite time average generally exists both if your system is finite or is infinite. And but okay, there are particular systems and classes of observers for which you can also define the limit in a different way. So if you take first the thermodynamic limit, so infinite system, then also the limit of infinite time exists at the level of expectation values. So not average, but just the expectation value approaches a stationary value. Then okay, we the second hour we use the time average state to infer the size of the space which is spanned by the non-equilibrium state during time evolution. And what I mean with that is that okay, you imagine this is the Hilbert space. Now you psi follows some path in the Hilbert space, and then the idea was to find the minimal set of orthogonal states, which are these points, such that you can approximate the state at any time with a given accuracy. And the question was, how big is this number, the number of states? Yeah? And an idea to answer this question was to define, to consider the time average state like this, in the limit of large system size, large L, large number of sides. Then, okay, this operator here can always be diagonalized. Okay, it's a density matrix, so in particular has this form. These are just the eigenstates of the time average state, and these are the eigenvalues. Then, by convention, I'm imagining to sort the eigenvalues from the biggest to the smallest. And then, okay, if I want to approximate this operator with a given accuracy, what I have to do is just have to keep the eigenvalues with maximal value and to disregard the smallest eigenvalue. So in other words, I'm truncating the sum up to a given value. Maybe I call m, or here I call the d dimension we are interested in. And the constraint is that we want that the sum of the eigenvalues that I keep is 1 minus some error they want to keep, and they want to fix this error. Then, okay, we try to solve this problem, which generally is kind of extremely complicated if you want to solve in a completely generic system. But now we realize that if our system satisfies some condition, in particular the logarithm of the overlap between the state at different times scales is proportional to the system size, to L, then there are many simplifications in the limit of large L. And in particular, computing the moments of this density matrix, you can infer the distribution of the eigenvalues of the operator. And if I remember well, we arrived at this point. So we derived the distribution of eigenvalues. And well, you can see there the shape of this distribution. So this is the sum over J of the eigenvalues of the time average density matrix times the Dirac delta function, lambda minus lambda J. And then you see that its omega here is this omega is this constant. So omega scales as the square root of L. It's very large. So one important feature of this distribution is that it becomes 0 for eigenvalues larger than a very small number, which scale it goes to 0 in the thermodynamic limit. Okay, so it's non-zero only close to 0. because okay, the eigenvalues are between 0 and 1. 1 is very, very far away from you. And then, okay, it has the shape, it has this kind of logarithmic singularity at this extremal point, and then, okay, the probability goes in this way. And, okay, having access to this, we can also compute now the number of eigenvalues. For example, the idea was we fix the error.
So this function changes with time, right?
Yes, exactly. If you increase the time, yes.
And
this is normalized. So if you
shrink, it goes up.
Yes,
okay.
Exactly. It's a distribution, so it goes with the time. It's expected because if you increase the time, that you are averaging over more states, so you expect that
somehow the states with lower eigenvalue becomes more important.
Yes, the lower yeah. Okay, so this is the distribution. Now we wanted to cut the eigenvalues up to starting from a given lambda, which corresponds to lambda d of there is t of the time here, and I call this error epsilon t. So we want to fix this area here, which is the integral distribution. This determines this lambda. Then we want to compute the number of states, this t, that give this kind of that correspond to this truncation. And what we have to do is now we have to consider the integral over lambda of the sum of the delta functions, because this is just the sum over all the eigenvalues, this quantity. You can still infer from the distribution, and you find that this quantity behaves in this way. Okay? You identify lambda epsilon t, and then this gives you the desired number of states. You do this, and then you realize that the number of states is okay. So if you have to solve this system where the integral distribution is equal to epsilon, and then you want and then you have to compute, this defines lambda, and then you want to compute the integral from lambda to 1 of that integral, and then you finally find that this d, this dimension, dt for given epsilon t behaves like the this behaves like how does it put it? Okay, somewhere. Not here. Okay. Okay, it should be something like root e2 over pi times the inverse error function 1 minus epsilon to the 1/2 and the time. Should be something like this. Now I don't find it. Here. 2. This is what you find. Okay. Well, this is your error, and then you see that this dimension increases with the time, as you can imagine, and then but it scales just as L to the 1/2, which is the square root of the logarithm of the Hilbert space. So in practice, you are visiting a very, very tiny part of the entire Hilbert space during this time evolution.
L is the size of the system.
Is the size, but then if you consider this as spin chain, then it's totally else. That is the size, yeah. And okay, so I want to show you some numerical results, some numerical check of this formula. And for example, here I consider the quantum quench, where the initial Hamiltonian is just the missing Hamiltonian. where the magnetic field is in the y direction. Notice, so it's a bit different from what you generally do. And then I consider this very kind of generic Hamiltonian, when you recognize there is an x, y, z interaction. And then I also put some magnetic field, some field in the x direction, some staggered field in the z direction, just to be sure that there was a completely generic system. Okay? And then I really consider very, very small chains here. So actually I could do it very easily with my laptop. I'm not an expert in numerics, so I just wanted to check the result. And then I plotted this dimension of the space that I want to, the number of states that I need to consider to describe time evolution with a given accuracy. So I plotted the numerical evaluation of this dimension against the prediction. The prediction is valid only in the limit of very large L. So you see here that even for extremely small system size, when you increase L, the data seem to approach the correct the results that we found. So when this wasn't really immediately expected because these are really small, so it's a completely different limit. So, but apparently it seems to work, and I consider also other Hamiltonians, so it seemed to be really in good agreement. And then, what I did, I wanted to check, because the next step is to check whether indeed, if you fix somehow this error in some way that we'll discuss in a moment, whether I can keep the accuracy on the state somehow controlled. Okay, and indeed here I considered the overlap between the state and the basis that I'm choosing, the reduced space, and I plotted here the error, so it's 1 minus the overlap, as a function of the time. And for the particular choice of epsilon theta that I will discuss in a moment, then you see that the error seems to be very stable, so it doesn't decrease with the time, and it's always bounded from above. So actually I'm really...
why yes to mean this?
Okay, the fact that it's symmetric about T over 2 is just a mathematical, but why it's really, I don't know, it's...
why is maximum at the boundary?
Indeed. Clearly the boundaries are a bit special points, but I really don't know. I always found this, the simulation, and I don't have really an answer to why the boundaries...
So basically at equal 0 is the initial state?
Yes. So apparently this approximation is such that it creates a bigger error at t equals 0 and the largest time in the interval, and then you keep instead the other error very...
But say it again, why is symmetric?
It's symmetric because, here you could reverse the sign of the time, and so the result was completely independent of the sign. The variance of the Hamiltonian is independent of the sign of the Hamiltonian, so you should find the same result.
I see.
So it's, but still, I don't know why it's generally maximal. The bound.
You remember what value of epsilon did you take?
Yeah, here. Okay, this is indeed I'll come back later. I consider this epsilon t as a function of the time, and I make it scale as 1 over square root of t. Why I did this? Okay, this is related to the fact. I don't want to fix the error on the. Here I fix the error on the time average state, but I would like to fix the error on the state. Now, generally, if you assume that the error somehow is, if you put some error in the average, and you assume that it is this produces an error on the sample, which is almost independent of the time. Then what happens is that, so if you want to imagine that the state at any time is like a random variable, independent random variable in every time slice. If you do this, then you realize that the error on the average should scale as 1 over square root of the number of points of the dimension of your sample. And this means that our dimension of the sample is proportional to the time in our case. So if I want to reproduce this kind of, if I want to keep the error on the state fixed somehow, I have to make this epsilon t to scale as the square root, 1 over square root of the time. Okay, this is just a statistical way of guessing the formula epsilon t. And clear then here you have to introduce another time scale because this is dimensional, so there should be some delta t here. What is the typical time scale? Well, this clearly depends on the kind of observables that you consider. And in particular, this delta t could be just as a small time window where you can distinguish the state for the observer you are interested in. And for example, if you consider local observables, generally you see that in the thermodynamic limit they don't vary much in a very small time window, which could be, for example, the delta t of your simulation. And then this just, so epsilon of the unit of delta t gives you the error in this small slice, time window, where you can't decide whether the state is in psi t or psi t plus tt. Okay, if now you assume that epsilon t scales in this way, what you find is that dt scales in the following way, in the limit of large time. It scales like square root of logarithm of t times t, and then there is L to the 1/2. This is a bit strange, no? Because okay, y should scale in a different way than linear, and indeed this is only an upper bound. Okay, that's true. Because there is, in fact, immediately we can see that there is a procedure to decrease this dimension of the space. What we can do, for example, is to, instead of consider the time window 0 capital T, we divide this time window in very small slices. So you have 0t. Now we split this in n parts. Let's call this delta t, like in the other case. Then we can apply our result for the small delta t. Our result is just that delta t appears here. So this becomes a constant, if you want. So it becomes a constant times t, times the time. Now the space spanned by the state can be obtained by merging all the states for the single slice. So you have, for this slice, you find some states here. Here you find other states, and so on. Now, if you consider the span of all the states, this is an upper bound for the dimension of the entire space spanned by the state. So in other words, what I'm claiming here is that if you just use this procedure, you find that this is just an upper bound, a kind of large upper bound that increases with the time. But this can be immediately improved by imagining to split the time window in this way, and then you find that the sides of dt, the sides of the dt, the number of states we have to keep in order to have an error epsilon on the state. Now this is the error on the state. Then is smaller or equal to, okay, this is just an upper bound, to this object here, 2 e2 over pi r function minus 1 minus epsilon. Okay, which is a more expected result. So now we have an upper bound that scales, which is proportional to the time, at least. But what is I want to stress here that this upper bound is very small. Okay, it scales as I repeat, as the square root of the logarithm of the Hilbert space. So extremely, you can visit only a very small part of states in this time evolution. Okay, let's keep.
Somehow, to rephrase what you say, is that a small fractional state contribute maximally to the time average density of state, the density matrix.
This now is a statement on the state itself, not the time average.
Okay.
Yeah. So I'm saying yes.
But it's the number of states that contribute to the density matrix, or in terms of probabilities of eigenvalues.
Yes. So it means that most of the Hilbert space will be you won't consider the time evolution of the state. You can just ignore most of the Hilbert space. You just have to take track of this very tiny part. And okay, so this result holds true in the limit of large L, and here you have correction which scale, okay, now I'm not sure, but it could be order of this, relative correction that goes to 0 in the thermodynamic limit. And so now the question is, what happens if we try to compute the same dimension, but now in a finite system, and we leave the time to be very large, so in the opposite limit of the diagonal ensemble. Okay? So we want to apply the same procedure, exactly this, but now the time can be much larger than L. Okay? So it's a completely different limit. So what does this tell us? This tells us how much what's the dimension of the space that can be spanned in extremely long time windows for a finite system. Okay. So how many states you will see? Oh. So now what you have integral, you have to compute this of the state. We already did the last time. And then, okay, if you express this in the eigenstates of the Hamiltonian, when we find that this is equal to the sum over the energies of the overlap between the state with energy E and the initial state, squared, here you have the diagonal part. And then you have another part, which is of diagonal elements, E different from E prime, and you have the overlap between the state and the eigenstates of the Hamiltonian, and then when you integrate over the time, you find this part, I. So now, this is the result. Now let's assume that the time we are considering L is finite in a spin chain. So if you remember, we defined something which I call delta, which was the minimum energy, was the, how we call it, delta, I don't remember, delta. Minimum over all the eigenstates of the difference of the energies. I introduced this, maybe it was in capital letters, more than. Okay, now we can use this, the existence of this minimum in a finite chain to bound this term, the contribution from the second term. And so in particular we can compute, okay, this is by definition rho bar t, the time average. So we can compute the norm of rho bar t minus this term. Partially we already did this. So, well, E, say 0 squared E. Okay? And then we just have to bound this part. So the upper bound for the overlap is just 1. So you have that the sum of this is more or equal to the sum of the absolute value of this. So you bound this by 1, you bound this by 2, because it's phase minus 1. And then you bound this by using this result, and the minimum value is delta. Yeah. So what you find is that this is more or equal to twice the dimension of the Hilbert space, which in our case will be just the if you consider a spin S chain, then it's the dimension of the local space. So this is the dimension. This is the dimension of local space. Space of the spin S plus 1, and then you have to the L power, the number of sides. So this will be this divided by delta t. Now you see that in the limit of very large time, this approaches 0. So this means that if you are interested to approximate the state again with the given accuracy epsilon, then we can drop this term and just consider the diagonal ensemble. Okay? So I'm just saying what we already computed last time, that in the limit of very large time you can completely neglect the fluctuation of the respect to the diagonal ensemble. And now, so what's the answer to our question? How many states should I consider now to keep the error fixed on the time average? And then you see here that it's very large. And the reason is that when you consider quantum quenches of global parameter, this object here, the overlaps, decay exponentially with the system size. So this object behaves like e to the minus L, would be some parameter alpha e, depending on the energy. And clearly on this state. Since they are exponentially small, this means that you need an exponentially large number of states to approximate the diagonal ensemble. So you see the difference. And now if we consider this limit, then you have to keep track of all the overlaps of a very large number of states. If instead we consider the other limit, when the time is large but the system size is larger, then the dimension is much smaller, it's extremely small. Yeah? So even when the diagonal ensemble gives the same result as the infinite time limit, from a theoretical point of view, it seems to be much more convenient to consider the limit of infinite time in the limit after the thermodynamic limit. Okay. So okay, this was just to show you the difference between how people define relaxation in our community. So there is a part of a community that like the idea of considering time averages, and instead another part of the community which is more stuck into statistical physics. So he prefer to take first the limit of infinite, the thermodynamic limit, and then studying the expectation value in the limit of large time. And now I want to let's see something in practice. Okay, which are the difference between these two approaches in a simple model. Okay, because this was very abstract for generic Hamiltonian. Let's now consider
just
yes.
Before we move on, just a question on this bound. Somehow, this tells you that this number of states contribute to the density. Of course, it doesn't tell you which state, right?
That's
somehow,
yes.
It's really that you get. So, in some sense, maybe those are states which are the most entangled. And I mean, if you want to imagine that, I'm trying to think how to put this together with ATH.
Yes.
And if you want to, your system is generic and will thermalize, means that these states are, the number of these states is small, but these states probably are high energy states in the middle of the spectrum.
Yes.
Or,
yes, probably that they will.
so in some sense, it's hard to make this a tool of approximation. It's not that you can truncate your Hilbert space to this size. And
I agree.
Right.
It's the dimension is independent of the details.
Sure.
The states depend. Okay. And moreover, okay, there is something maybe something I should stress that here it's completely general. No, we found this upper bound without assuming anything. Now it is known that if you consider a chaotic system or so-called integrable system, then you expect a different complexity in the time evolution. So this maybe could suggest that if you consider specific classes of system like integrable, then you can find a lower, a tighter upper bound for the dimension. Because okay, there are many symmetries in integrable systems. And this is indeed the system I will consider now a simple model. But this is just now. What is important is that even if it's an upper bound for a generic system, it shows you that this dimension is very small. This was the purpose. Okay, now for the following, I start considering a very simple model, a simple model of free fermions. We assume that the fermions don't have a spin, degrees of freedom, so they are called spinless fermions. So you can see spinless fermions. And they are described by in the second quantization by some creation operator. C dot L that create a fermion at position L, and they satisfy the usual algebra of fermions. So you got this N equal del Ln, and then you have C dot L, C dot N equal CL, Cn equal 0. So this is our the Hilbert space. You imagine that the Hilbert space is the Fock space is generated by this operator. So in particular, it means that the basis of the space will be this operator, strings of this operator acting on the vacuum. This is our basis of the space. And then, okay, we consider a very simple Hamiltonian in this system. The Hamiltonian, it just has an open term, which corresponds to the kinetic part of the energy. So we consider a Hamiltonian of the form an Hamiltonian like this, minus J. This is an energy scale. Sum L from 1 to capital L, C dot L, C dot L, plus 1 plus, oh, that's not C dot here, C dot L plus 1, CL, and then let's put also some external magnetic field like this. Probably you have seen this Hamiltonian many times, I guess, most of you at least. So notice in particular that this Hamiltonian conserves the number of fermions. So the fermions can just move from one side to the other, to this term, and then I imagine there is also an external magnetic field that tend to magnetic field. There is a chemical potential. Let's say. And okay, this model is quadratic in this operator, and every time that the model is quadratic, it means that it can be easily diagonalized, because you can simply diagonalize the model by linear combination, by redefining your fermions in this case. So it means what you can do in this particular model, because it's translational invariant, then the first thing that you can imagine is that to the right, the fermion is the momentum space. Likely this will diagonalize, or it will simplify the Hamiltonian enough. In this case, we'll diagonalize the Hamiltonian. So what you do, you can define some operators that create fermions with a particular momentum k. You can define them in this way. For example, L equal 1 to L e to the I Lk C dot L. Okay? Now, this is just a Fourier transform. So we can also express this operator in terms of the C dot K. And then what you find is that the inverse transformation is simply given by 1 over square root of L sum over K of e to the minus Lk C dot K. So what is K? K is K is defined in such a way that the e to the Ik is equal to 1. Yes?
Questions. CL plus 1 is equal to CL.
Oh, yeah, this is not an important question. I forgot this. Okay, you see that here the sum is from 1 to L, so for the sake of simplicity, now we assume that the C dot L plus 1 will be equal to C dot 1. It's equivalent to C dot 1. So these are called periodic boundary conditions. Instead, okay, just for your knowledge, if C dot L plus 1 is equivalent to 0, then this is called, usually in this context, as an open boundary condition, also free boundary conditions. And then you can have also cases when you have a minus sign here, and it's called antiperiodic boundary conditions. Okay, we consider periodic boundary condition. This is the reason why we have to find momenta satisfying this condition. Because when you consider here L equal capital L plus 1, you have to recover C dot 1. And this gives you this condition. Lk should be equal to 1. Lk, sorry. Okay, so if we rewrite the Hamiltonian in terms of now of the C tilde k, what do we find? Well, not really surprisingly, we find that it's diagonal. is equal. If we plug this expression there, then we have 1 over square root of L sum k of e to the minus I Lk sigma k times 1 over square root of L of sum over p, say e to the I L plus 1 p sigma p tilde. Then you have minus twice h times 1 over square root of L sum over k v to the minus Lk c tilde k and times 1 over square root of L sum over k of e to the I L p c tilde p. Okay, this is what you have to do. You plug the definition inside the Hamiltonian, and then what you realize here that you have to sum. You are summing over L these spaces here, and so these spaces give a contribution which is proportional to L only in this case if this k is equal to p, and the same here. Only when k is equal to p. Otherwise, you have the sum of phases which averages to 0. Yeah. So what you find is that the Hamiltonian is simply given by 2j sum over k equal 1 of h minus cosine of k c. So you see, this is an extremely simple model that can be diagnosed in one step, just in Fourier transform. And what does it describe here? It describes the Fermi C, because if you plot this is generally called the dispersion relation. It's like this. So she's generally defined as epsilon k score is called like this, and then if you plot it, epsilon k is a function of k, you find, depending on the value of h, something like this. Okay. So it means that in particular, the fermions with a small momento have a negative velocity, negative energy, and instead the fermions with a sufficiently large momento, they have positive energy. So if you are interested in the ground state, for example, the state that minimizes the energy, what you have to do, you have to create all these fermions, and this is why it's called it's a Fermi in the Fermi. So because they all contribute with a negative energy, so they decrease the expectation value of h. Okay, but this is not relevant. Okay. So this is the Hamiltonian that we are gonna consider in a moment, and then we would like to study time evolution under this Hamiltonian. So we want now to consider a particular class of initial states, and we could imagine, for example, to study quantum quenches where the initial Hamiltonian is similar to this one. Okay. It's still quadratic in the Fermi. So you can imagine that there can be some terms like C dag L, CL plus 1 like there. There could be terms like C dag L, CL, some coefficient here. There could be terms also that do not conserve the particle number. So you can imagine like a BCS Hamiltonian. So you can have terms like this, change, and so on. Okay. We want to study this kind of quantum quenches because if the initial state is the ground state of this Hamiltonian, then the calculation can be done exactly. Okay, just for the sake of simplicity. And what's the property of this Hamiltonian? Why these are simple? Because they are always quadratic in the Fermions. So this means that if and there are no broken symmetries, what you have is that the ground state of this Hamiltonian is given by a so-called Slater determinant. Okay, and well, it's a determinant, which means that if you are interested to compute, so if psi 0 is the ground state of H0, what you have is that you can you can express all correlations between fermions. So you can imagine that you are interested in some expectation value of fermions as a function of just the 2-point function of fermions. C that C that C tag, and so on. C. This is a simplification due to the quadratic form of the Hamiltonian. This is for the ground state. And because we want to study the time evolution under another quadratic Hamiltonian, this property remains. And this is usually called the Wick's theorem. So that allows you to reduce the expectation value of all correlation in terms of the 2-point functions. Okay, we will see, I think next time we will study more in detail quantum quenches within this model. Today I just want to use a result. Okay, so we don't derive it. I just tell you something, and we will draw some conclusion from the result. So what I want to tell you is that every time that you consider this kind of Hamiltonian, and imagine also this Hamiltonian has a reflection symmetry, which means that if this is your chain. Now imagine to revert all the sides, the first sides with the Lth side and so on. So you reverse the chain, and then the Hamiltonian is invariant. So let's also assume that this Hamiltonian is reflection symmetric. Okay. Then what you can prove rather easily is that the ground state of a generic Hamiltonian, I'm not specifying the coupling constant, yeah? So very generic Hamiltonian can be written like this. Psi 0 is equal to the product over all momenta larger than 0 of some coefficient which depends on the initial state, it depends on the initial Hamiltonian and the final Hamiltonian. Applied to the vacuum. So this was the vacuum of the fermions we defined here, and here the same fermion that we defined there. So what I'm saying is that when you, independent of the parameter, when you compute the ground state, then this can be represented in this way. And then clear, okay, your parameter enter here. These are the parameter of the system. This is called, okay, this is generally called the squeeze state, and can be generalized also to interactive model, but you see, it has this kind of Gaussian shape. And what do we want to do now? Okay, this is the state at the time 0. Now, if you want to compute the state at the time t, it's very simple. Okay, because now in this representation, you know how this operator time evolve, because these are the operator that diagonalize the Hamiltonian. We wrote it. Yeah, let's write it again. Sum over k of h minus cosine k of c that k ck. So what you find is that when you apply e to the I e to the minus IHT c tilde k dag e to the IHT, you immediately see this is something that you can prove as an exercise. It's very simple. Then you find that this is equal to e to the minus I epsilon of k t times c tan k. Okay? So they time evolve in a very simple way. So using this result, we can immediately write the state at the time t, which is this. Sine delta k over 2 plus I sine delta k over 2, and then we have a factor e to the minus 2 I epsilon of k t where here I use that epsilon k is even. So epsilon k is equal epsilon minus k. So this is why I have a factor of 2 here. Okay. Okay, so we have the state at the time t. Yep.
Just a question. I'm a bit confused. The C tilde are not the same fermions, right?
Yes, are the same fermion. What do you mean? Same as before.
So I mean,
of
the eigenfermions of the initial Hamiltonian.
Yes, they are. Of the of the final Hamiltonian. These are.
Yeah, but you're writing the.
That's true. This is the ground state of the initial Hamiltonian, but no, independently of the parameter, you can always express this ground state in terms of the operator of the final Hamiltonian, sigma k, if you want, this operator, and this is the vacuum of these operators, defined as C tilde k 0 is equal to 0.
Okay. So I guess maybe the other, let's say, Bogoliubov angle is hidden in the vacuum.
Yes, exactly.
Okay.
Yeah. Generally, this is what you want.
Okay.
Everything is encoded here in this coefficient.
That's the new vacuum after the Bogoliubov transform.
No, this is before. This is just the vacuum of in the XX model. Oh, XX, sorry, in this Hoping model, this pre-fermion model. This is just the vacuum of the C tilde k that I defined here. So I'm not really using anything. The initial state appears only here. This is the initial state. This depends on the initial state. The rest, no.
Okay.
Depends on all the final Hamiltonian. So this is a very nice representation because then you can immediately see at least how to write the state at the time t, which is just this. So you see that the form of the state remains the same, and this is related to the fact that in this kind of system, the Slater determinants remain Slater determinants when you consider time evolution, if the Hamiltonian is quadratic. Okay, but since we have this nice representation, we can also compute, for example, the diagonal ensemble in this system. Okay, the diagonal ensemble, so we can compute this. The limit t goes to infinity of 1 over t psi integrand d tau psi tau psi tau rho by infinity. What is this? So we have to so this is the limit t goes to infinity of the the integral from 0 t d tau over t of the product over k of cosine delta k over 2 plus I sine delta k over 2 e to the minus 2 2I epsilon k t, and then here you have again the bra, which is this k, let's say p cosine delta p over 2 plus minus I sine delta p over 2 e to the 2I epsilon p t, and then you have, I forgot the operator, c tilde dark k tilde dark minus k, so you have here c minus k, c k. Okay, I guess that's it. You have to compute this. Now when you take the time average, because the epsilon k, this is the product over k larger than 0. So the dispersion relation is a monotonous function for k larger than 0. So what you have is that here, in order to have a non-zero average, these two phases should cancel. So k should be equal to p. Okay?
The last k is p.
Right. This is k. Okay, if you consider for each k. So what does it mean? That this is the vacuum of this is the projector on the vacuum, no, of the fermions. How can you write the projector on the vacuum? The projector on the vacuum is clearly the product of the vacuum, the projector on the vacuum of the single momenta, k. So this is the product over k of the vacuum of the Fermion scale. Is this clear or not? So you want, here we define the vacuum as the state such that annihilates all the Ck. Now, in particular, I can imagine it as a state of as the tensor product of the state, which is annihilated by a single k, which I called 0k. So this acts only on the space of a single k, and this is defined like this. Okay, like this. Then what I can do is that the vacuum of all the fermions implies that the vacuum of the fermions is defined as Ck, if I consider now the tensor product of all the k here, k1, k2, and so on. This will make the job, because this operator acts only on the space associated to k, and by definition, this is annihilated by C. So what I'm saying is that the vacuum is simply given by the tensor product of all this vacuum on the single spaces. And so this implies that the projector on the vacuum can be written in this form, just factorized. Yes?
I'm a bit confused. So size 0 is the parameters that appears there. Is length h, for which so h is the
repeat the subject, sorry. What is size
so the parameter that appears
is
size
this
0.
delta?
Yes, so then the h, so h is the parameter h0, the original Hamiltonian.
Yes, you have the
But then
H.
side t, what appears there is delta h or delta k.
H enters
no,
into
side
k
K.
and also enter into delta k. Delta k depends both on the initial Hamiltonian and on the final one. Initial state plus H. Okay. You in this function here, you have information both about the Hamiltonian, which is now a free Fermion Hamiltonian, and information about the initial state. Then the operator instead depend only on the final Hamiltonian in this representation. So this is the vacuum of the operator that we defined before. So what I was saying that the initial state enters all here.
Okay, but what about the side t?
Side t.
So is this the same?
What would this
Oh,
say?
The wave function, psi t.
Side t.
Yeah.
Okay, yeah.
So is it the same parameter delta h?
Exactly. Yes, it's the same. Because when you compute the time evolution here, okay, I forgot maybe the phase related to the fact that
Psi t is just e to the ih applied to psi t.
Yeah, but then in the next slide you have both delta k and delta p.
yes, just because okay, yeah, you have to write psi the cat psi tau and the bra psi tau. Yeah.
You can call
Yeah,
it k
that's
t.
a tau. Yeah, that's a tau. So for the cat I use a variable k, and for the other I use p just to not.
But they still
confuse them.
depend on the initial state.
Yes, this depends on the initial state
Okay.
everywhere. Okay, it's just that. Okay, now. Now, so now we use this as well, and we use the fact that the time average constraint p to be equal to k. So what you find is that this rho bar, this time average, the diagonal ensemble is equal to the product k larger than 0 of the cosine delta k over 2 plus I sine delta k over 2 e to the minus 2I. No, there is no. Okay, let's write it this way, and then let's see. Epsilon k tau. No, tau. Okay. Okay, that's the answer. It's cosine square delta k, which is this term, applied to the projector on phi k of the of the vacuum k
Sorry?
Yes?
But the cosine term is independent of exponential of energy and...
Yes, it is.
And it should not affect on
That's true.
delta and k. And
This is why when you consider time average here of this, term, no?
Yes.
You have a contribution from this, and this is independent of time. So in the time average, it just appears like itself, which is this term that I'm writing here, cosine squared. This times this.
Okay, but why then k equal to pi here? It should not be the case. I just want to say that k and p should be independent. You should
Yeah, they're independent. Now imagine, that's true, but then imagine when you, okay.
It is the same product.
Okay, then let's do the step. Okay, let's make the step, because otherwise we are confused.
No, but you see that there is a square over there.
Yes, but it's just diagonal term. There is a should be like delta 1 multiplied by delta.
Yeah, okay.
No, but it is like this. It's product of k, product of p, and you're just rewriting as a product of the square.
Okay, I see.
Right? Is that
Yes,
correct?
yes.
Yes, I'm doing that. Then compute the time average of this. Okay. And then what happens is that when you compute the time average, because of the property of epsilon, you realize that all you have ways to cancel one epsilon with the other one. But okay, you are partially right, because here, if you imagine you have a product of the elements, so you will have indeed you have terms where it appears all the sum of epsilon in some sequence of k, and you will have the same here. What I'm claiming here is that if you want to zero those terms, which is related to the generality of epsilon, when the epsilon is sufficiently general, then in order to cancel them, they must be equal. Okay, yes, you are right. I see the problem. So, and what you find so with this, okay, there is some, okay, you're right. Let's try to mild assumption. Mild assumption. Of independence of epsilon, okay? And then you find the diagonal ensemble, which has this form, so cosine squared plus sine squared over 2, and then you have c dot k, c tilde k, the vacuum k, and then here you have c you have here c minus k, c k. This is your time average state, assuming the independent commensurability of the epsilon k. Okay.
There must be a tilde on the c, on the last two c's.
Can be.
There must be the tilde on the last tilde.
The tilde, exactly, yes. Thanks. Okay. You have this. Now, if you want, you can rewrite this. Okay, you have a projector on the vacuum of the fermion K. This can be explicitly written in terms of the fermions. It's very easy to prove. And well, if you want to do more exercises, it's really something simple. So you can prove that this is equal to C tilde K, C tilde. Okay, this is the space K minus K. C tilde minus K. Times C tilde deg minus K, C tilde deg K. This is a representation of the vacuum in terms of the fermions. And you immediately see that when you apply Ck on this, is equal to 0, because there cannot be, you can't remove two fermions in the same state, power principle, and even if you apply C minus K. Indeed, okay, this I should have defined. The correction here, when I defined this phi k, there was also this. I want to define a state that annihilates both Ck and C minus K. Okay? Okay, so you use this, and what you find that this term is just given by C tilde k, C k, C tilde minus k, C minus k. Okay, it simplifies a bit. Now you see that this is a kind of simple, simple operator here because it's the product of so the diagonal ensemble generally is a very complete object, and we can express it in this model like just the product of smaller objects defined in a spin 1/2 in a 4-dimensional space, K-scale. So not bad. And but there is a problem here because we started from a Gaussian state, from a slated determinant. Okay. Now, if you well, you can see that if you in this state, the Wick's theorem doesn't apply. So we started from a state where there is a Wick's theorem. So you have in particular, you reduce all correlation in this 2-point function of the operator C. Now we compute the time average, and you say, okay, does the Wick's theorem hold? And the answer is no for this operator. So in general, what I mean, for example, is that a result of this Wick's theorem is that if you have 3 to 4 operator like this, for example, then the expectation value of this is equal to C-1, C-2, C3, C4 minus C-1, C3, C2, C4 plus C-1, C4, C-2, C3. So this is one this application of the Wick's theorem to this particular correlation. So you see that you reduce this to always expectation value of 2 Fermis. Now, and so in particular, if you consider this quantity minus all this is equal to 0. Okay? So this holds true at any time. Now we compute the time average state, and it's not true anymore. Well, how is this possible? It's possible because when you compute the time average here, we are not averaging 0. We are averaging this, and then you average here separately. So you lose the Wick's theorem for these Fermions. Now I could tell you that in fact you could.
You get the argument?
Okay, this argument.
Yes.
Why it's possible? Okay, because when you clearly the average of 0 is equal to 0. But what happens is that when you compute the time average state, what you are doing is that you are replacing the state here by the average.
Ah.
So you are taking the average here, right? But then you are taking separately the average of this and the average of this.
Okay.
So this becomes different from 0 in general. And this also even if you have 2 slated determinants, you take the sum, it's already it doesn't work anymore. In this particular, for this particular quantum quenches, one can show that in fact this is a slated determinant, but in terms of other Fermions. Okay, so but we don't care about that. So just notice that some correlation.
Can you say why you say this doesn't because they are for Fermions?
No, yeah, no, this is what you have to do the calculation. You can, for example, consider here. You compute the correlation. You compute the expectation value of this, for example. You try to apply the Wick's theorem, and you find a different result. This you can compute also here because it's very simple, and then you find that you find different results. So this, in particular, you can prove that this correlation is non-zero. Okay, and so.
But what is the physical meaning of this density matrix average over all time?
This was okay.
I show it doesn't hold to some basic property.
Yeah, but what I when I introduced it, I said okay, there are cases, but there are the cases that we consider that in which this time average coincide with the limit of infinite time in the thermodynamic limit, and so this becomes. And then in a moment you will understand what does it mean, because here you see there is a problem. Because we have that at every time some correlation are non-zero in our state, but now we consider the time average and they magically become non-zero. So clearly the diagonal ensemble doesn't describe this correlation correctly, if you want. So what happens is that there are particular observables that are described in the correct way. Other observable, no. Okay? So this is why I stressed since the beginning that it's important to consider a particular class of observables you're interested in. Because you are seeing here indeed that there is some property you are losing, and you would like not lose this property because it's something you can see at any time. Okay, and so even in the limit of infinite time, you see this property. And indeed, okay, let's see what goes wrong here. What goes wrong is that we didn't use indeed the property of the state, for example, the property that remain in the infinite time, in the limit of infinite L. So, for example, what instead we could do is say, okay, at any time the state is Gaussian, is a state determinant. This we know. Now you consider your small class of observable O, which have the property that the limit L goes to infinity, limit t goes to infinity exists of the expectation value of this. This limit exists. So this means that if the time is very large, then all the expectation value will be will approach a stationary. Oh, this is not zero. Exists the limit. Okay. Will approach some stationary value. Okay. Now, but the Wick's theorem exists at any time. So if the time is just large, it's a very large number, then we still know that this state should be a slated determinant. So if you want to describe this, it should have the properties of a slated determinant, it should satisfy the Wick's theorem. So what you can do is that, okay, in order to be such in this way, then if I want to describe the stationary values of my observable, I need to consider a state, a particular density magnetic, which satisfies Wick's theorem. So it must have a form like, should be a quadratic form of the Fermi, the exponential of a quadratic form of Fermi. It should be a Gaussian. So in particular, you can have something which is, well, I don't know, some quadratic form times the observable. So this is, here we are just using the fact that at any time the state is a slated determinant, so we are enforcing the Wick's theorem. So the state should have this form. But now we want that the state should be independent of time. So this means that here, well, we should have something which is stationary. Okay? So this operator Q that appears here should compute with the Hamiltonian. Yeah?
I'm sorry, I don't understand what you... No, the limit of the limit, what are you doing?
The limit, because it's a double limit.
Yeah,
first,
oh,
sorry. Is the opposite, okay, yeah? Sorry, you're right. This is equal. Inequality. So first the thermodynamic limit, then the infinite time limit, and then here, this is Wick's theorem should hold at any time. So if we take this limit, this should have this form. And in particular, because it's stationary, it becomes independent of time, then this Q should be stationary, should compute with the Hamiltonian. So the question becomes, well, what can be this Q? How can we determine it? And well, this problem was solved 15 years ago. I think that it's kind of simple, but anyway, it was in this context was solved by Rigolo, Cheny, and collaborators. And what they propose is that in this kind of cases, Q should be a linear combination of the quantities that are conserved in this model. What is conserved in this model? Well, if you remember, the Hamiltonian was diagonalized by the occupation numbers. It was written like this. This operator commute with the Hamiltonian. Is it clear? Because using the algebra of the Fermions, you see immediately they commute. Because C dag tilde CK, C dag P, CP is equal to delta KP C K C tilde P minus C tilde K C dag P C K C tilde P, which is equal to delta KP tilde K minus, what is this? C to the k plus C plus CK, okay? And then you have I put this here, C dac P, C dac K, C tilde K, CP, and then you see that you can move this, okay, this is equal to, anyway, some steps, and then you see that it's equal to C dac P, CP, C dac K, CK. So they commute with one another. You can prove it in this way using the algebra. And so this means they also commute with the Hamiltonian. So you can easily prove H C tilde K, K is equal to 0. And so, since we need Q to be quadratic, okay, the quadratic operator that commutes with the Hamiltonian are these occupation numbers, then this Q should be a linear combination of these occupation numbers. So the proposal was that I tested clearly. This Q should be written like this: sum over K of some Lagrange multiplier times C tilde K plus cost for the normalization. Okay? So you see, this immediately follows from the fact that we impose the Wick's theorem in this particular model, and then now we imposing the Wick's theorem forces a lot the form of the state, and now apparently we have to look only for conservation laws that are quadratic in the fermions, and this is why you come with these answers. But then the problem, okay, maybe I can.
You can choose to stop. I don't have a break.
Okay, in a moment I finish now. Now the question is, okay, what is the criterion? Why here why this particular stationary state can be written in terms of the mode occupation numbers? Why these conservation laws and not really, for example, a conservation law like this? The product of two. Why not? Like in the diagonal sum. Here we excluded this because of Wick's theorem. But when you want to solve the problem in general for more complicated models, then the problem becomes to find a criterion to choose this particular operator Q. And so you see, so maybe it could be the fact that when you have the with a mode occupation number, you can classify all the eigenstates of the Hamiltonian, because if you fix all the occupation numbers, that you can really fix. They give you the quantum numbers for your system, so they form a complete basis. So this could be a possibility. You say, I found operators that commute with the Hamiltonian, and they generate all the eigenstates. Maybe this is the criterion. We'll see in a moment that this is not correct. Okay? But I give you 5 minutes first. Okay. This is the gist of what I was saying before. Okay. So we are considering quantum quenches in quadratic, in non-interacting models, or model can be written as quadratic form of fermions. And these models are special because the state satisfies the Wick's theorem. And so there are correlations that are equal to 0 by just for the structure of the state. And then we see that if now you consider time average, you lose the Wick's theorem. Okay? So without that, it will be observable. There will be correlations that are non-zero when you consider time average state, but they are exactly zero at any time. Okay? And so, and then this is related to the fact that when we take this limit, we should fix the class of observers we are interested in. Now, if we consider some observer for which the following limit exists, then because now the order of limits is first thermodynamic limit and then large time limit, then we have that the Wick's theorem should hold in this limit. So if we want to describe the state by stationary state, we should use an ansatz where the state will be a Gaussian. Okay, in any case, a Gaussian means that it's exponential of a quadratic form, and for all these states of this form, the Wick's theorem holds. Okay. This is a general statement.
Which state are you
The
referring to?
if now okay you have your what you want to do, you have your expectation value. You want to take the limit of infinite time. This becomes stationary, and so the idea is to, well, I don't need to keep all the information about the state. I can replace it by some different state which is independent of time. Okay? So I replace it with a state which I called rho infinity, and here I have the operator.
I see.
And then I wonder how to construct this state, rho infinity. And what I'm saying now is that rho infinity has some constraints, just because of the structure of our quantum quench. So it should be a Gaussian, it should be the exponential of a quadratic form, because we want the Wick's theorem to be satisfied in this limit. And then it should be stationary, because it should be independent of time. And it means that this operator Q should commute with the Hamiltonian. And so the question, okay, now I have to find an operator which is quadratic and commutes with the Hamiltonian. And we have a complete basis. We have the occupation numbers that can be used to generate all the bases. So we say, well, it should be the proposal is that it's just a linear combination of the occupation numbers. Okay? And then, okay, when was introduced this? I think it was introduced for an interactive model like this. So it was called the generalized Gibbs ensemble. Why? Because what you have is that if you remember statistical physics, the Gibbs ensemble is the canonical ensemble, the ensemble with the canonical representation, and you have this equal to the exponential minus the Hamiltonian times the inverse temperature. Here you have generalization, where this operator here is not the Hamiltonian, it can be something different, but it should commute with the Hamiltonian. So this is what was called generalized Gibbs ensemble. Okay? And originally it was written in this form, so you have to determine this conservation law. And the problem, as I pointed out before here, is that while in this problem, because it's simple, it's very simple to guess the formula. In more general model, this is complicated because we lack this kind of property, the Wick's theorem. So how can we determine what characterizes this Q? And first of all, I want to show that even this proposal is not completely correct. And it's very simple to prove it. Because, okay, for the Hamiltonian that we considered before, that I write again in the basis diagonalize it. So it was sum over k of h minus cosine k, theta k, c theta k. This is the Hamiltonian. Now, well, we can in fact choose different bases that diagonalize the same Hamiltonian. Because of the symmetry k minus k, so this Hamiltonian as epsilon k is equal to epsilon minus k. We found this. Then this means that I could define new fermions, which I can call R, for example, Rk, dark, which are just linear combination of C dark k and C dark minus k. So you consider this transformation. I define Rk in this way, k larger than 0, and Rk is equal to C dark minus k minus C dark k over square root of 2 for k smaller than 0. That's the definition. This is a unitary transformation again. So you can check that if you now consider the algebra of this operator, they satisfy the same algebra, the Fermion algebra. And now if you write the Hamiltonian in terms of this operator, actually you find the same. It has exactly the same form. So J, you can verify this, is equal to H minus cosine K, and now you have the operator R, that K, R, K. Okay, so it's just a different way to diagonalize the same Hamiltonian. Now the problem becomes, okay, if it's true that I just have to consider linear combination, then I could also choose this other one. Why not? This is a random choice of the way you diagonalize the Hamiltonian. And but now you see immediately there can be problems here. Why? Because now when you consider the occupation number of this operator, have a particular property. The property is that R dark k, Rk, is invariant under reflection symmetry. So you have this, and then when you reflect this is the momentum. No? So you can imagine when you reflect the chain, is simply change the sign of the momentum. Get the definition. So when you write this and now you consider reflection symmetry, what you find is that it goes into itself. Clearly, this is a reflection symmetry, reflection operator. That maps the side j into L minus j, L plus 1, okay, step from 1. This is the reflection operator. Then you apply this, you realize that in the momentum space, it simply means that you are reverting the sign of the momentum. And then you can check immediately that this operator are reflection symmetric. But so now this would mean that this operator here is always reflection symmetric. No, it's not the case, because if you start from an initial state which doesn't have this symmetry, then generally the stationary properties don't have the symmetry. And you can see it by considering now this other basis. Because if you consider this basis, you have operators that are not reflection symmetric, because you can check that this is actually trivial. So R C dot Ck is simply given by C dot minus K. C minus K. So one goes into the other. So if you rewrite the state, this e to the q, in terms of these bases, you can describe also states which are not reflection symmetric. If you do this, it doesn't work. So what's the criterion to choose why we chose here the mode of completion number? What is the important aspect that we have when we choose, for example, this basis, and we lose when you consider the other basis? This is the question. And now to answer this question, we go back again on the definition now. Now I go back. Now I define the kind of observables we are interested in. Okay? Because clearly all these results were depending. We are seeing all this kind of contradictory results just because I never mention what are we doing, what the expectation value of which observables are we considering. Now what I want to do is that we fix the kind of observables, and then we will ask again what is wrong with this R, K, and what is good with the other theta K. Okay.
Sorry?
Yes.
The model is integrable, right?
Yes.
And the CK tilde are not local when you
They are not local, yes.
So in principle, the density matrix has to be well, if you identify all the conserved quantities, and this seems to identify them, and that they are not restricted to be local, so the density matrix has to be conserving the local, not the local, the conserved quantities. Mm-hmm. So if all the conserved quantities are identified, then yes, the density matrix can immediately be constructed.
Perfectly right. The fact is that all these ensembles we consider are not written in terms of all the conservation laws. And the reason is that all the conservation laws are the projectors on the eigenstates of the Hamiltonian. And you have an exponentially large number of these objects. So when you instead try to define what's called generalized given ensemble, you are restricting a lot the subset, the set of conservation laws. And one way to restrict it, okay, I cheated a bit because I consider a simple model in such a way that there was a restriction due to the structure of the state. Immediately we saw that we should just consider the quadratic conservation laws. But still, in this case, we have problems related to the generals.
But it's just because one has to identify another symmetry, which is the reflection one.
Yes. No. It's
also, I missed something.
It's not that. It's more the fact that the solution of this. It will be clear in a moment. I will tell you a criterion for which you don't have to choose. You don't have doubts about what you have to choose. Okay? I don't want to tell you anything else. Okay. So what I say? Okay. what I want to do is to fix the class of observer. Class of observables. And the one I want to consider, if this is our spin chain, are the observable with the property that they act non-trivially, only in a small part of the chain. So what I mean with this is that you can write this observable as the identity on all the sides before a given point. Then here you will have some operator which acts on some range. Let's go. Which acts, for example, for the spins from the side L to the side L plus R. And then you have again in the rest the operator acts like the identity. Okay. This is what we call the local operator in spin chains, or if you want, also in lattice systems. If you now consider the operator with support in some surface or in some volume. Okay, so you say outside it acts like the identity. Inside it does something different. So these are called local, and okay, you have just to tell you, okay, these are local operator. Maybe in the literature you find also other definition. It can be useful in this context, like quasi-local. Quasi-local operator, it means essentially that your operator can be approximated by a local operator. So you can find the local operator, loc, such that the difference between the two can approach 0. Okay? You can find a sequence here of local operator, say depending on some index n, such that in the limit n goes to infinity, this operator norm approaches 0 sufficiently fast. So this is so you can approximate it by a local operator. These are called quasi-local. Okay? Okay, I don't write the exact mathematical definition, but this is essentially what people mean with that. So with the operator which have exponentially decaying tails, okay, instead of having just the finite support. Okay, so these are the observable we consider in particular this class. But everything I will say it also applies to this other operator. So we focus on this class operator, and then we ask now how to characterize the limit of long time, the large time limit for this operator. So what I'm interested in is to find limit t goes to infinity, limit L goes to infinity for this operator, expectation value of this. Now, because now we are considering this order of limits, we can actually use a bit the results that we obtain about the dimension of the space, how the spacing. Yes.
I'm sorry, I have a problem with your definition of quasi-local because you are already in an infinite chain. Otherwise,
yes,
all operators are quasi-local.
No, what okay. Let me write. You can imagine that we have an operator like sum over L on the sides, and then you have some coefficient here. Okay, sum over R. No, let's go this way. Sum over R of some coefficient CR, and then okay, let's just put an R here to tell you that the range of this operator is R. So you have this CR, and then there are operator sum over yes, the range. Okay. Imagine to write the operator you're interested in this way, so at increasing number of range of the operators. And then what I'm saying is that CR, if CR approaches 0 exponentially, CR behaves like the exponential minus R. This is R is the range of the local operator. Now, if this goes to 0 exponentially with R, then we say that this is quasi-log. And you can see that they cannot be approximated by a local operator because it's just exponential tails, then you cut it, and then you have just exponentially small correction. So essentially. you can define this in terms of norms, but it's not really important now. This is the idea. Okay, but well, if you don't want, this was just to tell you that if you find quasi-local, this is what we mean. It's very similar to local. And but we focus on this observation. And we are interested indeed in this particular limit. Because we take the limit of large L before, we can use the result on the dimension of the space. No? And in particular, we found that this dimension scaled as the times time L to the 1/2. So it was very, very small. So clearly this means that, well, we don't have to take to impose, for example, all the infinitely many conservation laws. You don't have to impose all the conservation law of the model if you want, okay? Because in this limit, clearly, all the expectation value of all the projectors are irrelevant. Because here, therefore, you need much less information that you get when you consider all the expectation value, okay? Or in the diagonal ensemble. So, but so which are the conservation laws that are important? Question. And in order to understand this, now I introduce something which is maybe could appear a bit a different topic, but that is related, and which is the Lieb-Robinson bound. Okay. The Lieb-Robinson bound is a very powerful mathematical result. So it was proven. This is not physics; it's mathematics. And this is about the time evolution of local operators, like this, in a local Hamiltonian of lattice systems. So you imagine an Hamiltonian H, okay, which can be written in the local means of interaction the support, which is finite. So it can be written like this, for example, in a chain like this, where the interaction is only between nearest neighbor sides, for example. And then you consider the time evolution of an observer, of a local observer like that, and in the Heisenberg picture. So you write this. Now, then, what happens when you consider this time evolution of the observer? Now, if I can show.
No, I see.
Switch it off automatically.
Okay, anyway, what I'm saying is that you can imagine to expand, for example, this expectation value in some formal series expansion for small t. No? And then what you find is that the first term will be the operator. Then you have to apply, there is an expansion in terms of commutators of this. So the first term will be the commutator between the Hamiltonian and the observer. Then you will have the second term, which will be the commutator of the commutator, the operator, and so on and so forth. Okay? Like this. So here I'm just showing a particular observer, okay, A, which is defined as some lattice in an epsilon trivially only on a given point. And here, just for the simplicity, I consider a Hamiltonian like this, which has only nearest neighbor interaction. Now you expand it, and then what do you find? The first order, when you consider the commutator, what happens is that because the range is finite, the new operator, which is the commutator, now has a support which becomes large. Okay? Then you go beyond, and then the next term there is another commutator. Every time that you commute, you increase the support of this operator by 1. And here we are just considering the serial expansion. So it means that at every small time t, you will have all this operator will have an infinite support, because you have to consider all the order of the expansion. So, well, so the problem is, what can we say about the time evolution of this operator? Okay, we can switch it off, I guess. Because what I want to show is an extremely powerful result. What I'm going to remind you is the Lieb-Robinson bound, which tells you that if you consider now define this as the operator at the time t. Okay? And this operator has support in a subsystem A, where A, for example, in the representation here, A is this. Okay? Is the interval. Interval L plus R. So you have your, this is your chain, and this is the side L, this is L plus R. This is where the operator is not trivial, and I call this A. So when I consider this, then the theorem states that now if you consider the commutator between the operator O A of t and O of b, OB is another operator, which is now in some subsystem B, which is defined here now. Okay, this can be a different operator. So it doesn't have to. Okay, so this can be bound from above by C. There is a constant here, something that depends on the length of the supports. Then it depends clearly on the norm of the operator, because if you multiply this by a constant, clearly this grows constant. So there is something which is the what is it? The norm of the operator, which is the maximum eigenvalue of the operator. And then here you have a bound which is exponential, so minus d minus v t over psi, where d is the distance between the two regions here. Okay? V is a parameter of the model. You can always find this V, this velocity, for any spin chain, and this is called the Lieb-Robinson velocity. Lieb-Robinson velocity. And here is another constant that depends on the model that you consider. But anyway, what you see is that this means that it's true that the operator at the time t becomes larger and larger. But in fact, in practice, the contribution from the tails, from the very, very large range, is very small. Indeed, it can be bound in this way. It can be bound exponentially. So this means that if you wait some time, what you have here, there is a lichen spreading from the operator. A lichen that move here at velocity vt. So the range somehow is increasing of the operator. But now it is practically, because for if the distance is much larger than vt, then this is exponentially small with the distance. So as long as this lichen doesn't touch b, then practically there are, this is equal to, this can be approximated by a local operator in this particular range, with exponentially small correction. Because this holds for any operator OB. I didn't choose the particular from OB. This is completely general. So so what I'm telling is that despite when you consider this perturbative, the series expansion, you see that all the terms that the support is infinity. As a matter of fact, the most important part comes from here. From support that increases linear in time. The rest is exponentially small. Everything is here. It's exponentially small with the distance. Okay? This is an extremely powerful result. Okay, at least from my taste, and there's important consequences. And in particular, it tells you that every time that you have an operator that can evolve in this way, you can approximate it by some local operator in a given time. Okay, why is this important? Because now, okay, if we were interested in the limit, in the expectation value of psi t operator psi t. Okay. Now the range of we can see this like the expectation value outside 0, e to the I ht or e to the minus I ht outside 0. Okay. Then we want to take the limit of large time of this, and we want to describe it through this generalized keeps on some O. In the limit, we can use that you remember that the dimension of the space goes in this way. And here you have the length of the chain. But now we can use this result to say that, as a matter of fact, I don't need to know the system very far away from my observer. Okay? Because it's just you have only exponentially small correction from L. So what I mean is that I can replace L by some effective length here. I can reduce L, some effective length that increases with the time. Then, to all intents and purposes, I can follow the time evolution of my observer. So this means that the effective dimension here will scale like, if we use this, we scale like t to 3 alpha. So I have to keep track only of what happens in this very small, in this kind of increasing subsystem. And now the question is, what's happening in this subsystem? There will be operators that remain constant. The operators are, for example, the energy density, because you can we are interested in what happens in some finite subsystem here. And then you can, if you write the Hamiltonian in this way, as I wrote before, HL plus 1, then you will have that this operator belong to the, for example, there could be, this operator could be here. So it's inside the subsystem. Now, since if you assume that the system is translational invariant, the expectation value of this operator is equal just by the expectation value of the Hamiltonian. Okay? The expectation value of the Hamiltonian is conserved, the energy is conserved. So this is a constant of motion. So this means that you can find all these operators. This is L plus 1, this will be Hn n plus 1. So all the operators that are here are conserved. So if you want to describe what's happening here, clearly you have to fix this kind of conservation law. It's important. And then, but okay, maybe in your system there can be other conservation laws. There can be something else that is conserved that belongs to the subsystem. So let's imagine that you have another charge, Q, which is written like this. And let's say that there's a range R, some different range. If this operator is here, then it gives a contribution, because it is in some subspace that is relevant for our limits. So that means I should consider it. So this suggests that we should, in fact, we should consider the operator that commutes with the Hamiltonian with some local properties. Because here we are saying that the relevant part is some subsystem. So only the conserved charges which have some kind of local density will affect my stationary values. Okay, they will clearly affect my stationary values. So, and also, as it was observed before, the mode of progression numbers are not local. They are all but local. They are completely localized. Instead here, this kind of argument is suggesting, look, you should consider the conservation laws which are local, not the mode of progression numbers. And if you do that, then you realize that in this particular model, the XS model, the local conservation laws are indeed written like this. Sum over k, or lambda k, theta k, ck, where lambda of k is some smooth function of k. So this is smooth. So you see, the result is correct, the one that we guessed, the original proposal, just to take the linear combination of the occupation numbers. But the reason is different from, it wasn't the reason because it's the space it described, it can be used to classify the state or whatever. The reason is that for some accidental reason, all the local conservation laws can be written in this form, in this model. Okay? And instead, if you use the other variable r, you don't have this property. So you see that they are describing actually some, there are local conservation laws that cannot be written with a variable r. So it means simply that you should add something. If you want to use the variable r, then here clearly you have to, this is not enough what we wrote, because it lacks some information, important information. So this to show that locality is the criteria.
Can I then say that more local operators contribute more? They are more important.
Yes. It's not well, it's not something I can show mathematically. But okay, there are studies. In particular, we analyzed the Daisy model after Quench, and we did exactly this. Try to see if you order the conservation laws depending on their range. Is it true that the most important one are the one with a smaller range? And the answer seems to be yes. Mm-hmm. So if you forget the conservation laws, so the error that you commit is larger if the conservation law is small. It has a smaller range. So it's really it seems to be the right order of to consider when you
Sorry?
consider this set.
I didn't understand completely because you do take the infinite time limit or the large time limit, of course, right? So so it seems that the locality could be eventually not.
That's okay, but now
I didn't understand the end.
Right. This is related to the how many of these conservation laws I have. So in general, as I told you before, if you consider all the conserved operators, you have something which scales exponential with that. No? Because all the projectors on the eigenstates, they are conserved, and they are exponentially large. If now I consider this kind of local conservation laws, and so I'm focusing now on integrable models, what you find is that there is a bound for these conservation laws. You cannot have as many as you want. You have something which is proportional to the number 12. It's linear in L. Okay? And so this is comparable with our estimated issue scale, like square root of L over there with the time. So it's just tell you that if you consider all of this, there should be enough. That's it. If there were not enough, so if you have just less than this and then you have other conservation laws, then maybe it could be a problem in other case. So in this way you find enough conservation laws to describe your system. As far as I know, there is no really mathematical proof of this so far. There are so only examples in particular model. It was proven in particular model, but it's not
in integrable or
in integrable systems. Yes.
And also something that I missed, but the C tilde are not local.
Yes. What makes them local is this lambda k. We can see it immediately if you want.
Can you explain it?
Yes. Okay. Let's write this in terms of SC, L, the original variables. So we take the Fourier transform of C times k. Okay. So
it's a specific linear combination. So the lambda are specific. I mean, they are actually a specific linear combination that would give that local.
Yeah. If you want really a local conservation laws, it should be a specific, which in particular here is just cosine and sine. Okay. Very simple. If you instead just consider a smooth function, then what you find is that you find a quasi-local operator with exponential tails. Just you can really see you go into the Fourier space here, and then you realize that here the coefficient. It's not with here. You write that the quantity that the weight of the operator with a given range is given by something like this. The Fourier transform. This is the range of the operator that you consider, and here you have a function lambda of k, something like this. Now, if this is a smooth function, then this decreases exponentially with r.
Okay.
So you have that they are quasi-log. Yeah. So yeah.
Okay, then inverse of lambda k should be just have a compact.
Yes, yes. It's something that goes to 0. And in particular, if here you choose cosine and sine, from here you see that you have only contribution from a particular range. Cosine of r if lambda k is equal to cosine of rk. When you take the Fourier transform, it just tell you that now this the range is fine. It's just a bar. And
But I do not understand why if you use RK operator,
yes.
You do not have local operator.
This is well, you can see it a posteriori. If you want. You can what I mean is that now you have, if you use the RK here, then you have apart from probably correction that goes to 0, you have some local operator, but you have the correspondence. So if now we imagine to write this sum over k of lambda k rk rk, okay, rk were very similar to c tilde k. They just have the term c tilde k plus c minus k. So here you have to consider also term where you have k minus k. And this term generally, I think that they are exponentially, they could be exponentially small corrections. So what I claim, but now I'm not doing the calculation, I didn't do the calculation, but what I'm claiming is that this can be written something local. There are some quasi-local conservation laws, Q local, say quasi-local, plus something goes to 0, plus corrections, I think. But what I mean is that when you consider all these quasi-local conservation laws, they are only half of all the local conservation laws that you have. So in particular, all the local conservation law will correspond to this particular value of lambda k, cosine rk. In this way, you are missing, this is missing, this is missing. This is missing conservation laws with a sign. Why I'm saying this? Because these conservation laws are all under reflection symmetry. And we know for sure that this operator here is even. So it cannot be, it's orthogonal to the other conservation laws. So you can't hope to obtain the other conservation laws from here. While I can tell you that it is the case for the sigma case. Okay? Okay, now that we know, well, at least I think that I persuaded you that the locality is a good criterion. If you are interested in local observables, in this class of observables, then I will have maybe, I don't know, I will do next time, I don't know. I will have to tell you how to compute now the conservation laws in your system, the local conservation laws, because this seems to be the important step to characterize the late time dynamics. And in particular, we'll consider first non-interacting system, quadratic system, spin of spins, so not Fermi, just spins, but you can see that is the same essentially. And I'll tell you a simple way to construct all the local conservation laws of this in these models, and then we, I think we will verify that they reproduce the infinite time limit of the expectation values. And then I will tell you how to do the same in the interacting case. Okay, what is the analog, which we'll see is very different, but well, anyway. And I'll show you some comparison between numerics and the analytic calculations. And okay, so with this I think yeah, because I can start now with the rest. If you have questions about something, you can ask because we have 3 minutes, few minutes. So I want to, just a comment because about the diagonal ensemble, when I compute the diagonal ensemble, that you have all this, Now let's go back. Because I did it very quickly and probably I lost many of you. And what I was saying is that when you remember, I wrote it like the product. There was a term plus some phase here. And here you had another product, okay? Another term plus another phase, minus sign. Now, if you imagine now you have all these products, if you expand it, you will have always some the sum of terms, which have this form: the exponential of sum over sum k, k1, kn, of the epsilon of kj, sum over j of kj minus 2it, and here you have the sum up to another m epsilon of pj. Now when you take the average, the time average of this, the only way to find something which is non-zero is that this the argument should become equal to 0. Okay? Now, so the question is, how can I make this 0? If I have a finite number of momenta k, and the epsilon k is sufficient in general, that the epsilon k are all incommensurable. The only way is that you have to simplify one by one all the epsilon. Okay? This is what I meant before. Here there is a mild assumption that here all the epsilon are kind of you can't form a linear combination of epsilon which is 0. So I'm assuming something that to the m of the calculation wasn't really important, because I wanted just to show that the diagonal ensemble doesn't have the weak theorem. So this was my problem. So you can imagine there can be complication here, but it's not really the point. Okay. Okay.
Well, you will talk next time about the Robinson bound more, or?
I will come back to that.
I mean, one question I have, but maybe you will talk about it.
No, then the answer.
Is it, so you said in general you can find the velocity. How does it work? I mean...
okay, what I can tell you is that the Lieb-Robinson velocity generally is larger than the velocity that you see practically in your system, the relevant velocities in your system. And in particular, okay, if you know something about interactive model, the velocities in interactive model, then you know that this velocity depends on the state.
Yeah.
Instead, Lieb-Robinson is independent of the state. So clearly, it should be an upper bound for all these velocities. No?
But it depends on the operator.
It depends only on the operator and the return. No, but not even the operator is not important. No. Only on the Hamiltonian.
Only on the
But it's an upper bound, and sometimes if you consider practical situation, it can be very large. I think I don't know. I never saw in. Maybe there is, okay, in this paper there are, in the paper I show you, not I can show you, there are some estimate of the velocity, but I guess that usually it's larger than the one that you see when you study time evolution. You see the emergence of lichens.
Okay.
It's always large. And okay, it just okay. I just.
But there is no, let's say, obvious, simple recipe to obtain the.
To think. As far as I know,
okay.
No.
It's a non-trivial.
Yes, I don't know how to do that. Maybe it exists, but I don't know. And because we are talking about Lieb-Robinson, I just tell you that it was generalized also to unbounded interactions. So, for example, you can imagine that instead of having a spin system with a finite local Hilbert-space, you can also put some oscillators, so some unbound Hilbert-space, and you can find an analogous bound for the velocity. So it's a slightly different definition. You have to define the Bayer operator and then you find a similar result. And that's just to finish with LibreOffice Unbound, just information about the importance of this. This was used for, if you can switch it, there is not. Because, okay, it has extremely powerful consequences, the LibreOffice Unbound, in several aspects of physics. And in particular, okay, it was used to prove the existence of the thermodynamic limit. Because here we always assume that the thermodynamic exists, whatever, and in order to do that, you have to use the LibreOffice Unbound. Then it was used to show that the correlations when you have a bounded system. So if you have a non-critical system and you prepare the system in the ground state, then correlation decay exponentially. This result, which is extremely very well known and important result, is proven using the LibreOffice Unbounds. Then, okay, also if you know the Lipschutz matrix theorem relies on the theorem, and then, okay, if you maybe know something about entanglement entropy, you should know that the area law, the famous area law, was proven using, again, the LibreOffice Unbound. And finally, okay, with this LibreOffice Unbound, you could prove that when you have inhomogeneities in your system, then you have the emergence of some Lacan dynamics. And you can also prove, using LibreOffice Unbound, that this generalized ensemble, that here we defined only to compute expectation values. It's also good if you equal time expectation values, I mean. It's also effective when you consider dynamical correlation function, so operate at different times. And here again, you use the LibreOffice Unbound. So this is a really fundamental result also in the field. It's extremely powerful.
And it goes back to the 70s, right?
Exactly. This is. Oh, I didn't. I escaped it. Anyway. Yes, it's 72, if I'm not wrong. Yeah. And then it was. What is fun is that it was proven before in quantum systems in 72, and I think it was generalized to classical system in after a few years, even 2 or 4 years. So this is the case where you put the theorem before and more complicated system.